Ever wonder how your phone knows which way is up or how a touchless faucet senses your hand? Get ready to dive into the world of microsystems and sensors,
Okay.
where tiny tech makes a huge impact.
Right.
We've got a stack of fascinating material to unpack today,
Yeah.
exploring how these hidden heroes are changing the way we interact with the world.
It's really quite amazing
Yeah.
how these systems take basic physics,
Yeah.
like pressure or temperature changes,
Yeah.
and translate them into electrical signals
Right.
that power our digital lives.
It's like giving our devices a sixth sense.
Yeah.
Our sources dive into all sorts of sensing principles, but
Sure.
today we're focusing on how these principles are applied in real-world devices.
Okay.
And we're kicking things off with a true technological celebrity, the quartz crystal.
Most people don't realize that quartz crystals are in almost every electronic device they own.
Really?
Yeah, these tiny crystals are the heartbeat of electronics,
Wow.
providing the precise timing that makes everything from smartphones to satellites function.
They're like the tiny drummers keeping everything in sync.
Yeah.
But how do they actually work?
It all comes down to piezoelectricity.
Okay.
Imagine applying a little bit of pressure to a quartz crystal.
Mm-hmm.
It actually generates a tiny electrical charge.
Oh, wow.
And just like a tuning fork vibrates at a specific frequency,
Yeah.
a quartz crystal, when stimulated electrically, will vibrate at its own unique and incredibly stable frequency.
So by harnessing this natural vibration,
Yeah.
we can create incredibly precise oscillators,
Right.
the timekeepers of our digital world.
Big.
It's mind-blowing how something so small can have such a massive impact.
Yeah.
But our sources hint that there might be a new kid on the block. MEMS resonators.
Uh-huh.
Could these be the next generation of timing technology?
It just might be.
Okay.
MEMS, or microelectromechanical systems,
Mm-hmm.
are like tiny machines built on a microscopic scale.
Wow.
These MEMS resonators offer some tantalizing advantages over quartz crystals,
Like what?
like smaller size, even higher precision, and greater resistance to shocks and vibrations.
So even more precise.
Even more precise.
Wow.
However, developing these tiny marvels is no small feat.
You're telling me.
Yeah.
One of our sources chronicles the journey of Desera, a company that pioneered MEMS resonators.
Mm-hmm.
They spent 9 years and over $60 million to bring their first product to market.
That's right. Designing and manufacturing these microscopic structures is incredibly complex.
I can imagine.
To give you an idea, imagine shrinking yourself down to the size of an ant.
Okay.
Now try to build a complex machine with parts that are 100 times smaller than a human hair,
Oh my gosh.
all while ensuring it can withstand the rigors of everyday use.
Yeah.
That's the challenge engineers face when building MEMS devices.
Talk about a delicate operation.
Yeah,
But as you said, the potential is huge.
absolutely.
Smaller, more precise, and more robust timing could revolutionize everything,
Yeah,
from smartphones and wearables to advanced medical devices and autonomous vehicles.
it really could.
It seems like with microsystems, we're constantly pushing the boundaries of what's possible at the microscopic level.
Absolutely. And speaking of pushing boundaries,
Yeah.
one area where microsensors are already making a tangible difference is in safety and security,
Okay.
particularly in the detection of dangerous substances.
Okay, now that's something I have to hear more about.
Imagine a device that can sniff out explosives
Okay.
with incredible accuracy,
Wow.
all thanks to sensors that are barely visible to the naked eye,
Now that's what I call putting microscopic power to work.
right?
How does that even work?
It's a fascinating application of MEMS technology.
Okay.
Picture an array of tiny resonators,
Mm-hmm.
each coated with a special material designed to attract a specific type of molecule.
Okay.
When a substance like an explosive comes into contact with the coating,
Yeah.
it actually causes a minuscule increase in mass,
Really?
which, believe it or not, changes the resonator's vibration frequency.
Wait, so by analyzing how the vibration changes, you can identify the substance.
Precisely.
Wow.
It's like a microscopic fingerprint for different materials.
That's really cool.
And what's even more impressive is that this technology has been miniaturized into portable devices, like the picosensor,
Oh,
which is revolutionizing security checkpoints, making them faster and more reliable.
that's incredible. It seems like these microsensors are popping up everywhere.
Right.
Making our lives safer, more efficient, and even more entertaining.
Absolutely. And we've only just begun to scratch the surface of what's possible.
Really?
For instance, let's shift gears for a moment
Okay.
and delve into the world of medical devices.
Okay.
Our sources highlight the MEMSTEC MPS-200G,
Mm-hmm.
a tiny pressure sensor that's making a big difference in healthcare.
Okay, I'm intrigued. Tell me more about this miniature medical marvel.
This little sensor which is smaller than a fingernail,
Wow.
can measure pressures with incredible precision, making it ideal for critical applications like blood pressure monitoring and dialysis machines.
Okay.
What's remarkable is its accuracy.
Yeah.
It can measure pressure changes as small as 1%,
Oh.
ensuring patients receive the right treatment at the right time.
Wow. That's incredible. Talk about a high-pressure job.
Right.
But it sounds like this sensor is definitely up to the task.
Absolutely. And what's even more fascinating is that the technology behind this medical marvel is based on a different sensing principle than the quartz crystals and MEMS resonators we discussed earlier. This sensor relies on piezoresistivity, which means its electrical resistance changes when pressure is applied.
So it's like a tiny stress ball for electrons.
Yeah.
The more you squeeze it, the harder it is for them to flow.
That's a great analogy.
Aha.
And just like there are different ways to measure pressure,
Right.
there are numerous other sensing principles that underpin this world of miniature technology.
Okay, I'm ready to expand my sensor vocabulary. What else is out there?
Well, we've got pyroelectric sensors,
Okay.
which generate a current when they detect a change in temperature. These are commonly used in motion detectors, flame detectors, and yes, even those touchless faucets we talked about earlier.
So the next time I wave my hand under a faucet, I'll know there's a tiny sensor in there reacting to my body heat.
Exactly.
That's pretty cool.
It is. And then there's thermoresistivity, where a material's electrical resistance changes with temperature. You've likely interacted with a device using this principle today without even realizing it.
Really?
They're used in everything from industrial temperature sensors to the thermometers used in healthcare settings.
It's amazing how these different sensing principles are being used in such diverse applications.
It is.
From keeping our homes safe to monitoring our health.
Absolutely. And what's even more exciting is how these sensors are being combined and integrated into increasingly complex systems.
Okay.
For example, our sources describe a fascinating application in the field of microfluidics.
Microfluidics, that sounds like something straight out of a science fiction movie. What is it exactly?
Imagine a laboratory shrunk down to the size of a microchip.
Okay.
With tiny channels thinner than a human hair.
What?
Carrying minute amounts of fluids.
Okay.
That's microfluidics in a nutshell.
Okay.
And it's revolutionizing fields like medical diagnostics, drug discovery, and even chemical analysis.
Okay, now my mind is officially blown. But how do sensors fit into this microscopic world?
Well, imagine you're working with these incredibly small volumes of fluids.
Yeah.
You need a way to precisely control the flow rate, temperature, and pressure.
Right.
Right. That's where microsensors come in.
Ah, so they're like the tiny valves and gauges in this microscopic plumbing system.
Precisely.
Okay.
And by integrating piezoresistive sensors, for instance, directly into these microfluidic devices, scientists can monitor and control these parameters with incredible accuracy.
Wow.
Enabling all sorts of groundbreaking research and applications. Now, that's what I call thinking small to make a big impact.
Right.
It's incredible to see how these tiny sensors are driving innovation in so many different fields.
Yeah.
But I have to ask, with all this focus on the microscopic, what about the bigger picture? How are these sensors shaping our understanding of the world on a larger scale?
That's a great question.
Yeah.
And it's something we'll definitely delve into as we continue our deep dive.
Okay.
Because as it turns out, these tiny sensors are not only revolutionizing the way we interact with the world around us, but they're also giving us a whole new perspective on our planet and beyond.
Wow. Okay. So we've journeyed deep into the world of microsystems, uncovering their hidden influence on our devices and exploring their incredible precision in medical technology.
It's clear these tiny sensors are already making a big impact. But I'm eager to explore your point about their ability to change how we understand the world at large.
It's fascinating, isn't it? Think about it. For centuries, our understanding of the planet was limited by what we could observe with our own senses or rudimentary instruments.
Right.
But now, with microsensors acting as our eyes and ears in even the most extreme environments, we're gaining an entirely new perspective.
It's like we've given our scientific instruments a sixth sense. What kind of insights are we gleaning from this sensor-driven perspective?
We'll take environmental monitoring, for example.
Okay.
Microsensors are being deployed across the globe to track pollution levels in our air and water, monitor deforestation patterns, and even predict natural disasters with greater accuracy.
It's like we're finally getting a real-time